We're going to get started with the last and best session. Thank you all for staying. My name is Sangeeta Bhatia. I'm a physician scientist in the Koch Institute, where I have the privilege of having many of the fabulous colleagues that you've seen already today in the physical building with me, which is just terrific. I there run the Marble Center for Cancer Nanomedicine, where our investigators think about using nanotechnology to find and treat cancer. I also am a member of the Electrical Engineering and Computer Science Department, where hardware meets software. And today, we're going to talk about the next step, which is hardware meets software meets the clinic. And so this session will be around machine learning into the clinic. The first speaker is Tommi Jaakkola. He is the Thomas Seibel Professor of Electrical Engineering and Computer Science here at MIT. He is also in the Institute for Data Systems and Society, as well as an investigator in the Computer Science and Artificial Intelligence Lab known as CSAIL. He's a AAAI Fellow. He has many, many awards and publications. And the title of his talk is Machine Learning for De Novo Drug Design. Welcome, Tommi.
Thanks for the introduction. So this talk is more methods-driven, talking about, in a very gentle way, our efforts in terms of developing automated drug design tools. This is perhaps a slightly different talk from others, also in the sense that the methodologies that we've developed have not really been developed in the context of cancer research, but will have implications for that as well. Before I get started, I should say a few words in response to the panel discussion. As someone who really understands the tools and comes from that side of the equation, and I would say that we are nowhere close where we can be in terms of the tools, and that includes also the talk that I'm about to give. So there is a great strides that we are going to make in terms of analytics and tool development over the next few years. So I'm very much looking forward to that. All right, so just a bit of background. There have been some recent advances in machine learning tools, from self-driving vehicles to superhuman game playing to machine translation. Now, the role of machine learning in these advances has really been to bypass what we don't know or we cannot calculate. So if you think about calculating moves in a game, if the game becomes complex enough, then we cannot do it, and we have to substitute predictions for things about future outcomes. Similarly, in machine translation, it's very hard to systematically assess how the semantics of a sentence in one language would be preserved as it's translated to another. But we can learn to bridge that gap. We can learn to map from one sentence to another from examples alone. So machine learning there plays a role of bridging what we cannot either understand or don't yet understand or cannot calculate. So the topic today is really drug design, and what enables us to do anything interesting in terms of automation here is the richness in the data. So if you think of, say, simple property prediction task, I have a molecule, I want to understand its properties in terms of solubility, toxicity, and others. In order for machine learning method to try to uncover the underlying physical relationship between the molecule and the associated properties, we need to have the data rich enough so that it exercises this mapping. Okay? So there's tons of data already available and being generated through small and large scale assays and curated databases and so on. The question, one question you might have is how much data is enough? Now, that depends greatly on the task that you're trying to solve. So suppose you narrow down the chemical space a little bit. You are only talking about, say, antibiotics. That's narrow enough, specific enough that you can get by with much smaller assays and still be able to do something useful. If you want a method that applies to the whole spectrum of chemical space, you really need big data to solve that problem. Now, our work on drug design is really a piece of a much larger puzzle that we are solving as part of a consortium that includes 13 major pharmaceutical companies, faculty from chemistry, chemical engineering, as well as faculty from computer science, such as Regina Barzilai and myself. The goals of this consortium are many. For example, we are trying to lift information from journal articles, notebooks, and others into a computational form so that it can complement more curated databases. We're trying to understand molecules, their properties, how to make predictions about molecular properties, how to optimize molecules. These are topics that I'm going to be talking about a little bit more as we go. We are also trying to understand reactions, what comes out of a reaction, how to optimize reactions, as well as how to manufacture chemicals that we want to produce. So I'm really going to focus here on a little bit on property prediction and more on molecular optimization. And this is going to be a very sort of a gentle introduction, hopefully, to the way we think about the problem and the types of tools that we are developing. So our problem really, broadly or framed ambitiously, is to take a precursor molecule and translate it into another version that satisfies design criteria, okay? And learn to do that from examples, okay? There are a few key challenges in order to achieve that. We have to somehow, either explicitly or implicitly, be able to predict properties of molecules. Okay? Otherwise, how could we search for a better version? Now, then we have to solve the more computer science problem of how searching for that discrete structure, the molecular structure that has the better properties that we want. We are actually going to not solve it in that way, but solve it as a machine translation problem. In one step, going from the starting molecule to the molecule that has better properties. There are lots of things that we should talk about in terms of understanding what these methods are actually doing and making them interpretable, and I'm going to touch on that topic very briefly towards the end. So let's start about predicting molecular properties. Many of the current approaches are now machine learning based, and the key problem here is to try to somehow look at the molecule, learn to read the molecule in the way that highlights the intricate features or combinations of features in the molecules that drive the properties that it has, okay? And we need to learn to read molecules properly. And what we are going to do is to try to explicate properties of molecules, learn to explicate those properties at multiple different levels of resolution. So let me just walk through very briefly in a sort of a caricature way how these representations arise. At the lowest level, we have a molecular graph. This is a 2D graph here. And what I would like to do here is to get a representation, a vector representation for each atom that somehow captures the context in which it appears in this molecule, okay? In order to achieve that, I somehow have to communicate the context around that atom to the atom itself. Now, I don't know what to pay attention to, how to actually do that, but what I'm going to do is to lay out a set of possible ways to solve this problem and drive the selection of which way is best based on the end task that I'm trying to solve. So a way of aggregating the features from the context is useful if it helps me to solve the end task, say predicting molecular properties. So we're going to communicate, send messages between the atoms here, get a vector representation for each atom. Then we step up one level further, look at larger substructures that appear in this molecule. okay, and how they are linked together. And now I want a vector representation, not for each atom, but for each substructure in that structure. All right, so what I'm going to do is a very similar thing. I'm going to drive that representation based on what's around it, what other substructures are related to it, as well as what atoms those substructures underlie. And finally, we have highest level of representation, which is sort of a loosely connected substructures, now losing information about the intricate connections between these larger pieces, but retaining some information about what they are and how they are roughly connected. And I get now a stack of vector representations at multiple different levels of resolution, and that is the representation for the molecule. Okay? So the way these are learned, then I get examples of molecule properties. They are mediated, the predictions are mediated by these multi-resolution representations, and I'm going to drive them so that I can make those predictions better. This, as an approach, once you've learned it, is already useful. You can do virtual screens, and this has actually been already quite exciting for us in collaboration with Jim Collins' group. There are exciting things to come soon. Now, our goal here is a little bit more ambitious. We don't just want to do virtual screens. We actually want to translate a molecule to a better version given design characteristics, the design specs, what we want the outcome to satisfy. This as a problem is very similar to a machine translation problem in terms of natural language sentences. And let me just illustrate that connection a little bit, hopefully helping you to understand how these methods work. So as a machine translation task, I have a sentence, say in English, and I want to translate that to a sentence in Spanish, okay? Most modern machine translation methods now are learned entirely from examples, having a sentence in English, sentence in Spanish, and lots of examples like that. And you learn that mapping, how to make that translation. What we want to do is exactly the same in terms of molecules, okay? Now, in machine translation, you can drive the translation to a different language that's analogous to design specification, what you want. You don't want a sentence in Spanish, you want a sentence in German, okay? What's not done, though, is having multiple combinatorial criteria here for translation. This hasn't really been done in the machine translation community in terms of natural languages. We are actually trying to do that, exactly that, in terms of molecules. Have design criteria that involve multiple different aspects, and given those criteria and a starting molecule, we find, say, a similar one that satisfies those criteria, okay? The big problem that we have to solve in this context is to somehow realize that novel molecule that would have these properties. So let me illustrate a little bit how this is done. It is essentially reversing the process that I explained in terms of how we get the representation in the first place. That's useful for prediction. Now we walk backwards and build the molecule from top down. Okay. So here I have some stack of these multi-resolution vectors corresponding to the precursor that I have, as well as a target specification of what I want to come out. Then I'm driving that to decide which substructure should I start with, okay? It's just a single substructure. It's the same as all different levels, okay? Then I interpret what I just did. I'm going to use the same mechanism to derive a representation for what I now have so that I can decide what's left to do in terms of generating the molecule. Then I'm going to decide what's the next substructure and who it should link to, roughly speaking, then figure out the intricate ways that these connect, and then reinterpret what I've done so far. So you proceed until you generate the whole molecule in this kind of so-called auto-regressive way that you're building substructure at a time and connecting it to what you already have. Okay, so we call this programmatic translation when you are given a design set of design criteria, starting molecule, and you're supposed to generate a novel molecule that satisfies this. Okay. Now, how well can this possibly work? So let's see some examples of how well this works. So here, let's start with a very simple scenario that I have just a single criteria that I want. Analogous to translating just an English sentence to Spanish sentence. So I'm giving a single criteria, and here just a drug likeness. So I have a precursor molecule. I want to turn it into a molecule that's more like a drug in terms of statistical characteristics of that molecule. Okay? And what I'm showing you here is the success rate in percentages that the diverse set of candidates that the method generates as the possible target molecules, what fraction of those actually satisfies the target criteria that I have set. Okay? So this method is learned entirely from examples of a molecule, its correct, better version, examples of those, and then given a new molecule it has not seen before as a precursor, you need to translate that into a molecule that satisfies these properties. So you can see that the success rate here is about 80, and the bars on the left are competing methods. The bar on the right is our current method, and actually the last two bars are our methods, previous version, and the last one on the right is our current method. You can do this with different properties here in terms of bioactivity against a dopamine receptor. And again, the result is in over 80% of the candidates that the method generates are actually valid molecules that satisfy those criteria. Now, I talked about programmatic translation. So what we want to assess now is if I start directing the translation towards more combinatorial properties. So it would not just gearing it to solve a single property improvement, but a multitude of them. Okay? What you see here, again, the bar on the right, the last two bars on the right are our methods, and the other one is a competing approach. Now, what you see is that the percentages went down. So it's much harder to solve this task when you have multiple design criteria. That's number one. Number two is that this task was actually very hard, set up intentionally to be hard for the method, because it was learned from examples primarily consisting of single criteria improvement pairs. So you have a molecule, it improves drug likeness. You have a molecule, it improves bioactivity. But very small fraction of those training examples were actually multi-criteria improvements. So what this is testing is our ability to redirect the translation, creating molecules of the kind that it has not really seen that much in the training examples. So even in that case, 1/3 of the candidates that it generates actually satisfy the criteria, which is starting to get to a practical level of utility. Now, the last thing that I wanted to mention briefly is about understanding. We don't want to just generate methods that are black box approaches, however accurate they may be. You need to understand these methods, why they work the way they do, make them interpretable so that you can verify, you can diagnose problems, and you can potentially get new insights about chemical reactivity by understanding what was buried in the data that you may not have known before. There are basically two broad approaches to achieve that. One is based on essentially a local randomization. If you have a precursor molecule, you translated that to a valid target molecule, Now, if I randomize the precursor, then the target will change as well. And now I can do causal analyses of what drives the method to think that this is the right outcome, and diagnose what those dependencies are. That's number one. Number two, that's sort of a starting to be prominent in the field more broadly outside this context, is designing models to be self-explaining from the start. So they highlight the way in which they use information already as part of the architectural design. One way to make these methods better and also more interpretable is by incorporating physical constraints and chemistry more into the models rather than have them just be statistically driven. And we are in the process of doing that as well. So in summary, what we are building here is just a capacity to do molecular translation, directed programmatic molecular translation. So the methods here are quite broadly applicable, but were just demonstrated in a simple context. In terms of their utility for cancer research, there are many steps that need to happen here. For example, much better integration with our understanding of cancer biology in terms of what to target. So with that, I'm going to end and just show you some recent papers from this effort while you are waiting for the transition.